Hello everybody! In this video we're gonna showcase and explain a very simple and basic stack-based buffer overflow attack. So first of all, let's take a look on the source code that I have here of a vulnerable program. That's vuln.c. So in this program we see only one function, this is the main function, and at first we see that the program is expecting an argument from the user, otherwise he will get the message expect the password. So if the user provides an argument, this argv1 will be copied using string copy to a buffer, a character array of 256 bytes long. Then we have a comparison using string compare between key array and buffer array. Key array has the value password1, buffer array has the value that the user provided. If the comparison is successful, means if these two arrays are equal, the user will will see the message login successful. Otherwise, the program will print login failed, wrong password. And let's take a look at the actual functionality of the program. So I'm launching vuln without any arguments. I see the message expected a password. Now I will launch it with one argument called arg. I will get the message login failed. And now I will provide password1, which is the correct password, and I will see login successful. So the question now is, at where is this program vulnerable at? So let's take a look at the source code again. So as we said, the user input, that's argv1, will get copied into a character array named buffer, which has a fixed size of 256 bytes or 256 characters long. This will happen using the function string copy. At this line, we have to consider two cases. What happens in the case where the user input is smaller than 256 characters, and what happens in the case where user will provide an input, a string that is greater than 256 characters. For the first case, we have no problems. The program will execute normally, everything will be smooth and fine. For the second case though, where the user input is greater than 256, that's where we have a buffer overflow, and that's the name. So, to explain this further and be easier for understanding, we will show some diagrams. This is the first diagram. So, this is how a stack looks like. So, in the stack, we have the buffer, which is the allocated memory for our variables, for our arrays. For example, this buffer array will be stored into this area called buffer. In the stack, we also have the base pointer of the program, that's EBP, the return address pointer, and the name parameter. For the name parameter, we do not care that much. Let's leave it out for now. What we do care though is the base pointer and the return address. So, these are the low memory addresses. This is the stack, and the stack gets fulfilled upwards. So, this is the case where user will provide an input that's a string that's greater than the fixed size that we have here of our buffer, and the result is to fulfill or to overwrite the values that are on the base pointer, as we said, that's EBP, and the return address, which means that the user can control the return address of the program. So the program will not return 0, instead, it will return something that the user is able to control. So the question now is how to exploit that. So first of all, let's see if we are able to crash the program, providing some input that is longer than the expected one. I will keep this diagram up there on the top, and I will go to my terminal, and I will launch vuln, and I will start providing like pure randomness. We get the message login failed, obviously, and now it's time to provide input using a Python script. That's for the ease of use, because we cannot manually, obviously, write 255 or more bytes by hand. So I will use this line of code, which will provide to my input 255 capital A letters. So let's run vulnerable, and with input 255 A's. Here nothing happened. Let's keep increasing. 280. we get a segmentation fault. That's good news for us, not that well news for the developer of the application, because for providing input that is longer than the expected, we fulfill the buffer long enough so we overwrite some critical addresses, either the base pointer or the return address, so the program actually crashed and we can see a segmentation fault happening. So we first of all have to find where exactly the crash happens. So how many capital A's do we need in order to crash the program? Let's try 270, nothing here, 274, segmentation fault. So let's make 3, nothing. So at 274 we get our segmentation fault. Let's try to observe the same behavior in a debugger now, and we will use GDB for that. So let's launch GDB with the vuln program, and first of all let's make a normal execution of the program. We get the message login successful. Now let's try to observe the same behavior of the segmentation fault. So I will run it, and yet again providing input with Python. So 273 was okay. Yeah, we get the message that the process exited normally. So 274 crashed the program. So here we see this segmentation fault with this message and this return address. The blue one is the return address actually. And now let's make 278. So yes, I want to run this again. Okay, and now we have no message here regarding libraries and stuff, but we can see that the return address is 41414141, which means that we were able to control the return address, and the return address is actually the 4 capital A's. So which means that if we take a look on this diagram up there, the first segmentation fault that happened on 274 crashed the program but did not overwrite the return address. So we see a normal return address up there, but still a segmentation fault. That's because if you remember, the first one, that's BBBB, is the base pointer. And then if we write 4 more A's, so let's add a plus symbol, and I will write, let's write the letter C as it's up there on the diagram. Yes, we get a 43, 43, 43, 43, which means that we were able to control the return address. So if we want to be accurate with the diagram, that would look like, let me clear the screen, that would look like 270 A's plus 200 plus 4 more B's plus 4 more C's. So we're at 270 A's to our normal buffer. We write 4 more B's, that's x42, 42, 42, 42, to the base pointer, and 4 more bytes with the capital C letter, x43, on the return address. So now we will get a segmentation fault with the return address of our capital C's that we wrote up there. So now let's observe in the debugger the values on the registers. So we have to observe the base pointer. We can also observe the stack pointer and all the other registers that we want, the instruction pointer or whatever. So first of all, let's disassemble the main function. So here is the assembly of the main function of our program, that program actually. we will put a breakpoint in between string copy and string compare. That's where our point of interest is after string copy. So let's put a breakpoint onto this address, for example. So I will break here and I will execute the same. Yes, from the beginning we see that the breakpoint hit. So now let's examine. X stands for the examine. I don't know, let's examine 8 bytes on a hexadecimal and byte format of the base pointer. So actually let's examine 4 bytes. So you see our 42, 42, 42 here. This is our letter capital B. So we see that right now we are exactly watching the diagram up there. So our stack is fulfilled with capital A's, with 270 capital A's. Our base pointer has the value 4 times capital B, that's x42 4 times, as we can see up there, and our return address. So let's stack pointer. Basically, no, let's see the base pointer and let's see 8 bytes of it. So above, as you remember, above the base pointer is the return address. So this 4 bytes is the base pointer and this 4 is the return address. So that's exactly what we see up here. x43 4 times. You see, x43. So if, for example, now I continue the execution, I get the x43. So this means that at this point we are looking at the exact diagram inside our debugger. So let's go to the exploitation part right now. Let's imagine a case at which, instead of writing A's and B's and C's, things that make no sense at all, we fulfill the buffer with some shellcode that does some job. Let's say that's launching a shell or returning a reverse shell from a remote host, or I don't know, sending an email or whatever else it can be. So the shellcode will be stored in this area, the buffer area. Then I will use all this space plus the base pointer to do my shellcode thing, and then I am able to control the return address. So I will overwrite this with a value that will point to the beginning of my shellcode. So how to do this? First of all, there is a special instruction in assembly, which is the nope instruction, NOP, which means just slide, just do nothing. That it just slides the program. It's like not empty space, so it's not 0, but it's an instruction, a special instruction that's just sliding the program, like doing absolutely nothing. So I can start writing nopes here. Remember that the buffer field direction is upwards, so we'll start with nope instructions here instead of A. The nope instruction is x90, so not x41. We will write x90 instead of A, capital A, which is x41. We will write as many as we need. Then at some point somewhere here up there, we will start, it will be the beginning of our shellcode. The shellcode should reach until this point, so until the point that it overwrites the base pointer, and then I will provide as a return address the beginning of my nope sled. So the address where my nope instructions begin. So the program will try to return to this address, then it will start sliding upwards, and at some point it will hit my shellcode and it will execute it. That's the concept. That's the basic idea. So let's see how can we do this practically. So first of all, let's run the program with some gibberish stuff here. confirm that everything is working. Okay, exit normally. That's perfectly fine. So now let's disassemble the main function. So this is the these are the instructions of the main function. So we will set a breakpoint yet again to this address in between string copy and string compare. So we will break at that point, and now I will run the program providing as input argument via Python buffer. Okay, the breakpoint just hit. So now I will examine 100 bytes hexadecimal byte format of the stack pointer. So we see that the A's, that's x41 as you remember, start from this address, which is the B8, B9, BA. So it's B8, this one, B9, B10, not 10, BA. So start of the stack, it should be BA. This will actually be my return address. So this is the point that I will make the program to return at, and it will be a little endian format, which is actually reading the bytes backwards because the buffer fill direction is up, not down. So this is the first byte of the return address, the second one, the third, and the fourth. So it will be XPA, XCF, XFF, XFF. Perfect. So now we have the return address. This will be our return address. So now we have to define how many nopes we need, and then we will add our payload. So let's grab this Python input, and first we will do the nopes, how many, plus the shellcode, plus the return address. This will be the final format of our input. So as we said, we have already the return address. This will be the return address, which is the start of the stack down there. So we said that we are pointing right now down here to the first, very first capital A, but in this case it will not be a capital A, it will be a nope, and the nope will be 0x90. Then we have defined how many of them do we need, and then is the shellcode. So let's copy the shellcode. I have it ready here. The shellcode is 46 bytes, and to having the size of the shellcode is important because in order to find how many nope sleds we need, we have to subtract from the full size of the buffer plus the base pointer the size of the shellcode. So which means that if you remember, the very first segmentation fault came when I wrote 270 A's plus 4 B's, or 274 A's in total. It's the same. So for defining how many nopes we need, we will do simply 274. That's when we overwritten the base pointer minus the size of the payload, which is 274 minus 46. Perfect, which is resulting 228. So that's how many nopes we need. So we need 228 nopes, then it's the shellcode, and then it's the return address, which means that if we take a look on the diagram now, where is it? Yeah, there you go. Which means that instead of having A down here, it will be nope, 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 so many nopes until up there, somewhere up there, when it will be the beginning of the shellcode, which is this baby right here, 31, somewhere here it will be 31, and then it's the last 4 bytes of the shellcode, which will override the base pointer, so the base pointer will be 6E2F7368 up there, and then it's the return address, which will be BA, CF, FF, FF. So, without much to shed, we just delete the breakpoints, continue the execution, the program is not running, let's clear the debugger for the highlights and let's run this and let's see. Boom. And as you can see, the process is executing a new program that's user bin dash, and here this is a completely normal shell where I can type commands like who am I am root, I can cut the shadow, I can do anything I want basically. I can do an ls, I can do anything I want. So that's the concept. I hope you guys like it. So final part, let's examine what we said regarding to the addresses once more. So I will disassemble the main function. Oh yeah, I have to quit the GDB and launch it again, unfortunately. So let's see, I will run with some gibberish. Okay, disassembly main, it's completely fine. We're putting the breakpoint as we said. It's very awesome. And now we're launching our attack. So let's see. All right, awesome. Let's examine 8 bytes hexadecimal byte format of the base pointer this time. So let's see what's up there. So you can now see that the first 4 bytes of the base pointer, which is this part on the image, is the last 4 bytes of our payload. That's 6e. Oops. Let's put that always on top as well. So that's 6e. Yeah, here you go. 2f, 73, 73, 68, and 68 up there. And then, if you remember, right above the base pointer is the return address here on the image. It's the return address that we just provided, which is BA, CF, FF, FF up there. So deleting the breakpoint and continuing the execution, we yet again have a bin dash shell, like a normal shell where we can do any kind of funny stuff. So that was it. I hope you guys like it. Please leave a like and a comment and maybe suggestions on what you want to see in the future. Thank you very much.